we're going to try to get through as many of these as we can. So, my second page. Okay, so here we go. Number 25. So problem 25 in my mind has 3 parts to it, all right? So what's happening is you've got this block that slides down this little like quarter pipe, right? Okay, so the first part is the block sliding down the pipe, okay? Second part, it then hits this uniform rod. So the second part is the collision, all right? And then the third part is after the collision, the uniform rod is going to swing up as a result of the collision. Okay? So there are 3 parts. Slide, collision, swing. Good? Yeah. All right. So here's what we know. We know that the block begins at a height of 0.2 meters. We know the length of the rod is 0.4 meters. And then we know the 2 masses. So the mass of the block is 0.05 kilograms, and the mass of the rod is 0.10 kilograms. And then the collision, the block sticks to the rod. So everybody good up to there? Yeah. All right. So is everybody okay with my sort of breaking that up into those 3 chunks? Slide, collision, swing? All right, so what would be a good starting thing? Sure, get us started, Peter.
Well, you know that you can just deal with the block as of right now, so you know that it's just GPE at the top, and you can convert that into just KE at the bottom.
Awesome. So for the slide, we should be thinking in terms of conservation of energy. As the block slides down the ramp, you're going to convert GPE to KE, so that means MGH at the top has got to equal 1/2 MV squared at the bottom. Cool? Yeah. M's cancel out, so your V is just the square root of 2GH, which, if you're keeping score, gives you, like, it's almost exactly 1.98. Good? All right, so now we got to worry about the collision. So let's write this number down. So the velocity at end of slide is 1.98 meters a second. Okay, so now the collision. So what concept should I be thinking about here to do the collision? I'm not trying to ignore you, I just want, sure, Seba, what do you got?
The velocities will be the same, so you can do conservation of momentum or energy, right?
What do you think?
Momentum.
Yeah, momentum. Conservation of momentum. Does energy have to be conserved in a collision, you guys? No. So anytime you see 2 objects colliding, you should immediately go to momentum. Okay? You've got a block sliding with a rod, colliding with a rod. Conservation of momentum. What kind? Linear, angular? Angular. Okay? All right, so collision. So what we know is the total angular momentum before the collision has got to equal the total angular momentum after the collision. So the rod begins at rest. So initially, all I've got is the block, right?
Right.
So you guys remember we've a couple times now seen a shortcut for finding the angular momentum of a point particle. Anybody remember? Sure, Maggie? Yeah, MVR, MRV, yeah. So this is the mass of the block times the velocity of the block, which we just found. So I'll go ahead and put that number in. Times, what do I use as the R, you guys?
The 0.4.
The 0.4 meters, right? Is everybody cool with that? Because here's my pivot point about which my block is going to have angular momentum, right? Cool? So times 0.4. I don't know why I didn't put in the mass of the block, but whatever. All right, so that's initial, right? And then after the collision, like Sebo said, they both have the same velocity. Specifically, though, we should be focusing on the angular velocity, right? Because that's what's the same, is the angular velocity. Okay? So, angular momentum is I omega. So let's do the rod first. So the rotational inertia of the rod is 1/3 times the mass of the rod times its length squared, right? Cool? So that's my I times omega. Plus, now we got to deal with this stupid block. Can I do MVR or MRV or whatever it is?
No.
Not really, because,
You don't know the
well, I guess you could MRV and then just use a jumper. I don't know, whatever. So your I is mr squared, right? So the mass of the block times the radius squared times omega, right?
Doesn't it give us the mass of the block?
Yeah, I don't know why. Yes, it totally does. I don't know why I chose to not put those numbers in.
It's okay.
What do we got?
Sorry, what did you do on our side?
What did I do where? Here?
Double.
This? Okay, so this is the rotational inertia of the rod. It's 1/3 mr squared. Cool. Times omega. So this is the angular momentum of the rod after the collision occurs. Good. And similarly, this is the rotational inertia of the block times its angular velocity. Is that a genuine okay, or is that a, yeah? All right. Everybody good?
Yeah.
Okay, cool. So, any problems with what's up here? All right, and like Peter said, you're given the mass of the block and the mass of the rod, which for some arbitrary reason I chose not to write down. Do you guys all agree you can plug those numbers in and solve for your omega?
Yep.
Okay, so if you do that, that omega ends up being, that's the wrong sheet. Is it 2.97 rings a bell for some reason?
Yeah.
Is that right? Where did I put my sheet? Down over here. 2.97 radians per second. So that represents the angular velocity of the block rod system immediately after the collision is done. Good? Any problems with it? All right. So after our collision, our angular velocity is 2.97 radians per second. So now I think we've just got one last part to deal with, which is the swing part, right? So how should I approach this? Is this still conservation of momentum?
Nope.
Good. Conservation of energy, right? Everybody good?
Yeah.
Okay. So what type of energy do we have down here? Sure, go ahead.
Isn't it RKE?
RKE of what?
The block rod system.
The block rod system. So you got to find the RKE of the block, find the RKE of the rod, right? And then it's going to swing, well, I guess for my drawing, it's going to swing up this way some distance before stopping. At that point, what type of energy do we have?
GGE.
Just GPE, right? So my RKE initially has got to equal my GPE finally, right? And we're going to solve in some fashion to figure out what's going on there. So the RKE initially, I think that's not actually too bad, right? Because it's just 1/2 I omega squared, right? So let's do the rod. So that's going to be 1/3 times, I'll actually plug in the masses this time. The mass is 0.1 mr squared. So times 0.4 squared. I am really unhappy with this. And then we need 1/2, oh damn it. So this is 1/2 I times omega squared, and our omega we just found it was 2.97, right? Everybody okay with that? There's a lot going on there.
Are you recording?
Yes. You can tell because I'm swearing a lot. There we go, yeah. Okay, thank you for checking. All right, everybody good?
Yep.
All right, so that's the rotational kinetic energy of the rod. Now we got to do the block, right? So plus 1/2 I for the block is just mr squared, right? So that's 0.05 times 0.4 squared times, once again, 2.97 squared equals mgh. So there's a couple ways you can deal with the GPE. Before we get there, let's simplify this. So if you type all this garbage into your calculator, you get something that's on the other page that I foolishly misplaced. Oh, I don't know if I recycled it. I totally did. There it is. 0.1167. So our RKE initially, after you solve it, it ends up giving you 0.1176 joules of rotational kinetic energy. Yeah, it's here.
So at this point, can't you just plug in the MG, find the units, and then do some trade?
Kind of. So here's the deal. So we've got this. Oh, darn it, it came on tape. All right, but so you've got this system, right, where you've got this like block attached to a stick and it's going to swing up, right?
Yeah.
Like, okay. So I guess I see two ways of thinking about this. You can either treat the whole thing as a system. How would I deal with calculating the GPE of a weird-shaped thing like this?
Center of mass.
Find the center of mass. So option one is think back a couple chapters and figure out how you find the position of the center of mass of this rod with the thing at the bottom. Does that make sense?
Yep.
So that's one way of doing it. Or you can figure out how much the mass goes up, how much the pendulum goes up, and treat their GPEs independently. Which one of those ways seems the most intuitive to you guys? As soon as I said center mass, a lot of you guys were like, ooh. Do we want to do them that way, or do you want to do them separately?
Center mass.
Center mass? All right, let's do it that way then. Okay. So it actually, to be honest, it ends up not being that bad. When I did it, I treated them separately. Okay? But you can do it together. All right? So here's where we're at then. So we've got this rod with a block on it, right? So the mass of the rod is 0.1 kilograms. And the position of the rod's mass is, well, it's uniform. So I can kind of treat it as being at the center, right? So that's 0.2 meters from either the top or the bottom, right?
Yes.
Good. All right, and then we've also got the block. So the mass of the block is 0.05 kilograms. What do you want to call the position of the block? Do you want to call that 0 or 0.4? You see what I mean? Like, we need to make like a number line, you know?
Should we call it 0 since it's going to be height from the ground?
That's what I would do too, I think. Let's do that. Let's call this 0. All right? And that makes the position of the block 0. So now what I can do is I can figure out how far above the ground the center of mass of this system is. Does that make sense? Okay, so the position of the system is, well, it's a weighted average. So it's 0.1 times 0.2 plus 0.05 times 0 all over the total mass, right? So 0.1 plus 0.05. So what's that going to give you? 0.02 over... I need a calculator. So 0.02 divided by 0.15 gives you 0.13 repeating. All right. Let me pause there for a minute. Are we okay, Sabo? You okay? What do you...
I'm just not getting the same greens, but I'm probably just tripping.
You're not getting the same greens. Did anybody else get that number? For the, are you talking this?
Yeah, I keep getting like this weird 0.05 something. I'm just plugging it in wrong. Don't worry. Don't waste time doing it. Don't worry about that.
Yeah, well, I actually, when I was doing this, I was following the exact same steps, but like hitting different numbers.
Huh.
I think we should just.
So maybe it's just like me punching stuff like that.
Did anybody get that number? Because if it's wrong, we should figure it out.
Final try.
Oh, sorry. So real quick, if you're videoing, I calculated that wrong. I forgot my 1/2. So correct that. My rotational kinetic energy was wrong. All right. So what we just accomplished over here is we found the position of our center of mass. Okay. So it's 0.13 meters from the bottom of the rod. So what's going to happen is, so the whole rod is 0.14 meters. Here's that center of mass. So this distance here is 0.13. Cool? Oh. Oh, darn it. All right. So that it's going to swing up, right?
Yep.
But my center of mass is still relative to the rod. It's still going to be at the same spot. But what we want to know is, as it swings up, how far does it go up, right? So we want that little height there. Does that make sense?
Oh, makes sense now.
Yep.
I see what you mean.
Wasn't that the height that you would get by like dividing out the mg from the other side, and then right? Because like we just got the RKE, and so on the other side is still the GPE, and so if you divide out the mg, you get that h.
I don't know if I'm following you for some reason, because I think I'm trying to think ahead. Give me 1 minute.
Okay.
All right, so here's where we're at. So we've got our RKE. After a little debate, we ended up with 0.0588 joules, right? Good. So that's got to equal the GPE of this thing. So that's mgh, which I guess is what you're saying. So what's our total mass now, you guys? 0.15, right? Times g times h. And you guys all agree we can solve for h? So let's do that. So 0.0588 divided by 0.15 divided by 9.8. So the height ends up being 0.04 meters. So now how do we translate that to an angle? Well, yeah, a little bit of trig, right? So there's this distance here is the same as this distance here, right?
Yep.
And we're looking for this angle.
Yep.
So I guess we do need to know this angle, or this distance here. So the whole thing is 0.4. If this is 0.13, then this is 0.26 meters. Good?
Why wouldn't we subtract out the h right now?
I'm going to. Oh, yeah, okay, sorry. Yeah, I was thinking the whole thing. So minus the 0.4. So now we've got this triangle here, if you're keeping score.
Okay, I think I'm following. Yes.
Better?
Yep.
I think I'm.
Inverse cosine.
It's a 4.
So now we can do inverse cosine and find the angle.
Could we go over how you got that height? Not like the green stuff. 0.26
All right. So real quick, so do you agree that the center mass is going to go from here to here, and that vertical displacement is 0.04 meters, right? That's what we found here. Good? All right. So the other thing I know is I know that since I know this little distance here, oh, I wanted that to be a different color. This little distance here and this little distance here are both, what was it, 0.13 meters?
Yes.
Okay. Well, that means that these distances, oh man, why is, oh, there we go. This little distance here and this distance here, those two blue distances, both have to be the length of the whole thing minus 0.13, right?
Yes.
Okay, so those two blue distances are 0.26 meters. Follow? Is that a question, Sarah? Are you
That's a question, but not
you sure?
yeah.
I think I'm getting this.
All right, and so now we need to find a triangle for which we can find our angle.
Yep, got it.
So the triangle I looked at was this. I know that's 0.26. I know this is 0.26 minus the 0.04. Here's the other side of the triangle, so now you can find your angle. So, and then find your angle. Cool? Yes?
I just had a quick question. So, like, let's say, so the same amount of length that was on the bottom was on the top, you would just ignore, like, that when you're finding the gravitational energy? Like, if,
Say that one
so
more
there's
time.
the pivot point, and then there's the same length on the top as there is in the bottom. So when it goes like this, and it starts to rotate, you kind of just, like, ignore that, because, like, they cancel out.
I'm not following your train of thought. Say that when you say on the top, you mean above the pivot point?
Above
Are
the
you saying
above
like,
the pivot point.
so you're saying hypothetically, if
Yes.
the drawing had
You
looked
just-
like this,
yeah,
pivot
you just
point,
ignore that. Yeah, no, the same.
and then it had pivoted like this?
Yeah.
Is that what you're saying?
Yeah.
No, you would still have to find the position of the center of mass for the whole
But
mass.
if it's at the pivot point, then it was increasing, right?
Say that one more time.
If the center mass was at the pivot.
Oh, right. Yeah, then there'd be no change in GPE. Correct. Is that what you were asking?
Sure, yeah.
I don't believe you.
Well, yeah, well, never mind.
Because it said same mass above and below, right?
Yeah, so then,
Oh.
so then it would just be like the, never mind.
Then it would just be the black.
Yeah,
Yes.
That's what I was saying, yeah.
I gotcha. I understand. And I agree. Sarah.
Okay, so I know I did this problem like completely wrong, but I still got the correct answer, and I wanted to know how much of a coincidence that was.
Okay. There are different ways of doing this. When I did it for myself, I did not use the center of mass approach.
I didn't either.
Okay.
So I found like the gravitational potential energy, I subtracted by the rotational kinetic energy, and I subtracted it by like, I don't know, like 0.15 times 9.8 h.
0.15 times 9.8.
And then I found h, and then I found like the angle I found it, and then I got the correct answer, but I feel like that's not work.
I feel like let me look at it. Do you have a minute between this class and your next class, or no?
Yeah.
Let me look at what you did. I think we can explain why that worked, but I need to look at the numbers and see what you know what I mean.
Okay.
But I think you might be okay.
Because it took me like 2 seconds. But
Oh, I see. So you never did the collision, did you?
I don't know.
Okay. All right. I'll take a look. Now I'm nervous because I don't think you can do it in less than 3 steps. Because you have to find, you can't set the energy at the top of the thing equal to the energy after the swing. Because you lose energy during the collision. So, you know what I mean?
Yeah.
Okay. All right. Any other problems with this one? Okay.